Hi guys, welcome to my series of machine learning in Theano. In this tutorial, I will teach you guys about how to write a basic binary classifier using logistic regression in Theano. So a logistic regression can be used to build basic binary classification methods. So for example, if you have a data set of email of spam and ham emails, you can use logistic regression to detect, given a new email, if this new email is a ham email or a spam email using the features of your input email. So the basic building block of your logistic regression model, it's what's called a sigmoid unit. The sigmoid unit works as follows. So first of all, it takes into the weight vector and take the dot product with respect to the weight vector. It adds the bias term to it, and then it computes a hypothesis, which is nothing but 1 over 1 plus e to the power minus z. The curve of the sigmoid function looks like this. As you can see, as we are moving towards minus infinity, the y term, it's getting closer and closer to 0, and similarly as we are moving towards plus infinity, the y term is going closer to 1. So in certain settings, a sigmoid function can also be said as a squashing function, because it squashes the input range from minus infinity to the plus infinity to an output range of 0 to 1. Let's build some intuition behind what exactly we will want uh, from our logistic regression model, and let's define our cost function from that intuition. So since it is a binary classification problem, we will have two labels. So we will have label equals to 0 and label equals to 1. So in specifically in case of our spam detection example, we can give label of equals to 1 to our spam emails, and we can give label equals to 0 for our ham emails. So let's see what behavior we will want when our label equals to 0. So since this is our hypothesis function, we will want that our hypothesis function should predict something which is near 0 when our true label is equal to 0. So we want to penalize our model less when our hypothesis function is predicting something which is near 0, and we will want to penalize our model a little more when it is predicting something which is way away from 0. So if we use minus log 1 minus x, this function will give us the same behavior. So as you can see, uh, so this is the case whenever true label equals to 0, and as you can see, whenever our hypothesis is predicting something which is near 0, our cost is less, which you can see from this vertical distance. And whenever our hypothesis is predicting something which is near 1, our cost is pretty high, as like it's close to 2.5 or something. And similarly, what will be the behavior we will want whenever true label equals to 1? For example, for all the spam emails, we want that whenever hypothesis is predicting that it is near zero point 0.8 or zero point 0.9, we will want our cost to be less. But whenever our hypothesis is predicting something which is near zero point 0.01 or zero point 0.2, we want to penalize our model much more. So this is the behavior you can get from minus log x function. So this is the behavior you want whenever true label equals to 1. So you want to penalize the model more when your true label is 1, but your hypothesis is giving something which is near zero point 0.1 or zero point 0.2 or less than 0.5 basically. So this vertical distance is representing the cost, and you want to penalize the model less when your hypothesis is predicting zero point 0.8 and zero point 0.9, which basically means that it's making the right prediction. So if you combine these two intuitions together, you get this cost function, which is the mean of minus y log of h of theta x minus 1 minus y log of 1 minus h of theta x. And as you can see here, whenever the true label is y equals to 1, this component will become 0, and this part of your cost function will get activated, which is the behavior you want when your true label is equals to 1. And whenever y equals to 0, this part of the function will get deactivated and this part of the function will get activated, which is the behavior you want when your y equals to 0. So this cost function basically summarizes your intuition in a very beautiful way. Let's generate some classification data. So we can use make classification from scikit-learn to generate 10,000 samples. Let's split our data set into train and test set for evaluation. Let's generate some Theano placeholder variables. So we will take a matrix and integer vector, and let's define some initial values of our weight and bias terms, and let's define them as some Theano shared variables. Let's define our hypothesis function, which is nothing but 1 plus t of exponential minus t dot w with respect to x minus b. And so we have put the negative sign inside, so we are putting negative with both the dot product and the bias term. And we can define our prediction to be hypothesis greater than zero point 0.5. So everywhere where hypothesis predicting greater than zero point 0.5, we will label them as 1, and everything where it is predicting anything less than zero point 0.5, we will label them as 0. Let's define our cost function in Theano, which is nothing but minus times of t mean y t log hypothesis 1 minus y t of log 1 minus hypothesis. Let's define our gradients with respect to the cost function, and let's use the Theano gradient operator t dot grad for the cost function with respect to w and with respect to b. The last thing we will need to for training is define a train operation function, which will take as input the x and y, which will be our Theano placeholder variables, which will get populated whenever computational graph will be called. And let's define our output to be the cost, and let's define the to update operation. Since we have two variables here, we will have two tuples, one for the weight and one for the bias term. And let's define our prediction function, which will take into x value and give us the prediction value. Let's loop it through for 1000 iterations. Let's pass train and y train for training. Let's train it through, and let's compute the F1 score, which is 0.89 and 0.8832, which is pretty high for both the test set and the training set. So this was my tutorial on how to build a basic binary classifier using logistic regression. In the next tutorial, I will teach you guys about how to add regularization for parameters to prevent overfitting logistic regression. Till that time, take care.